Any questions? No questions? You guys been using these quizzes I put up? You have? But you have no questions on them. All right. I think I've gone over the bulk of what I'm going to go over from this chapter. There's a couple other things to include. So just as a roadmap, again, I'll write this, chapter 1, I would just say chapter 1 was all the numerical stuff. Chapter 2 was about atoms. And now when we start putting atoms together, we're making compounds. Ionic and covalent. Ions and ionic compounds, chapter 3. Covalent compounds will be chapter 4. We'll start after test 1. So what am I saying here? So we're not talking much about covalent compounds, but it helps to say a little just for the contrast. So here's an example of a covalent compound. I've just written this smaller right here. We will get to where we talk about what we call intermolecular forces, but really it means intermolecular attractions. And this is talking about covalent again, so we're not here. But intermolecular forces just sounds very, very sciencey, but really we're just talking about what are the attractive forces. So let's say I had a sample of this. This is ethane. Let's say I had a sample of this in a beaker. Really, this would be a gas at room temperature. And I kind of jumped over some things right at the beginning of chapter 1. But a physical process is something you already know about. Something going from a solid to a liquid and a liquid to a gas. That would be saying we had, say, a crystal of a bunch of these together, and then when we turn it into a liquid, we break the molecules apart and they're just kind of able to swim around each other. And then when you turn it into a gas, they shoot out away from each other completely, and they're completely free and away from each other. Quick description of a solid, liquid, and gas. You just picture those molecules stuck in place, kind of in a lattice, and that's a solid. It's a liquid if you put a little more heat in and loosen them up a bit, then they can kind of swim around and move around each other, but they're all still together. That would be a liquid. Heat it up some more, it becomes a gas. But bonds here, bonds among the atoms are really the lines you see. And the intermolecular relation between them, how much they stick to each other, is related to going from solid to a liquid to a gas. But notice, I started off as a solid, then I heated it up a bit, turns into a liquid, heat it up a little bit, turns into a gas. None of these bonds get broken. They stay these little units as molecules. They're like, this is a solid, then you turn them into a liquid, and they stay these little units. And then you turn them into a gas, and they stay those little units. So that's a physical process. Ions, I've done this before. Sodium, do sodium chloride again. Ionic compounds, to be a solid, they form this array of these alternating ions. Do you remember that? So it's a solid, and then you heat it up. To get these to free up and move around, you're talking about breaking the ionic bonds. We don't generally draw lines for these types of bonds, so I'll just leave it like that. But the bond here is the ions stuck to each other. So these are ionic bonds, and these lines here represent covalent bonds. So when you turn this from a solid to a liquid, here you're literally breaking the ionic bonds. The reason we define this as an ionic compound is because of the bonding. It's ionic bonding. It's literally positive and negative charges being attracted to each other. These little units aren't positive and negative being attracted to each other. It has more to do with sharing of electrons. But there's still a slight amount of attraction among these molecules. Nowhere near as strong as the attraction among these ions. So, and the electrostatic attraction, that is positive, negative ions being attracted to each other, is way stronger force than what's holding these together with these little lines. Even the force in between these, the intermolecular force, is pretty weak, very weak, compared to the bonds between these ions. So if you just read these paragraphs, it tells you ionic compounds, you have something very cold and it's a solid. You warm it up some, then it becomes a liquid. You warm it up more, it becomes gas. So these form a solid, but if you want to melt them, you have to heat them to tens of thousands of degrees just to get these ions to loosen up and start swimming around each other. Much less heat it up even more and have an ionic gas. So one thing about a property of ionic compounds is they have extremely high melting temperatures. That pretty much means they're always a solid unless you're on the surface of the sun. Like in a natural state, you have to be on the surface of the sun. Even fire itself doesn't tend to be enough to melt any ionic compound. So ionic compounds, you can just think of them in general, are just kind of always solids. Unless you put them in something and make them dissolve, which you can do. But just as a pure substance, they have extremely high melting temperatures, so that you barely even see these as liquids anywhere in the real world. In a lab, of course, we can create heat sources and make molten ionic solutions, but for the most part, an ionic compound is just pretty much always a solid, certainly at room temperature, but even way above room temperature, even in your oven at home, you can't get these to melt, much less turn into a gas. Whereas molecules, the range is all over the place for all the many and very different molecules you could have. Some have very low melting points to go from a solid to a liquid. Some are liquid at room temperature. Some are still solids at room temperature, and you've got to get them a little higher than room temperature to get them to melt. And then, of course, heat them up some more, you'll turn them into a gas. But generally, molecules, you can break these bonds with just heat, but you have to get these to tens of thousands of degrees. So tens of thousands of degrees just to turn these into liquids, much less a gas. And these, by the time you get tens of thousands of degrees, just about any molecule is already going to be a gas, and then you start literally degrading the molecule and ripping it apart. So really, the fact that there are such different entities, ionic compounds and covalent compounds, they're almost incomparable when it comes to trying to think of these as physical changes. Because you have to get them so hot just to get them to melt, they're pretty much always going to be a solid anywhere you're going to see them in the universe. So that's very high melting points is what I'm getting at. Ionic compounds have very high melting points. Many ionic compounds are soluble in water. After saying how extreme you have to be to get these to come apart, they actually, many of them dissolve very easily. Some do, some don't. So it's kind of a wishy-washy rule, but we'll get to talking about things dissolving and other things. We haven't gotten there yet. But you can dissolve molecules and things, and you can dissolve ionic compounds and things and break apart the ions. But that has more to do with the power of the solvent than it does putting a bunch of energy into it. So just that general stuff about physical properties I have to mention. That's another thing. More on polyatomic ions. So I figure most of what we need to do is just review ionic compounds, bonding ions, ionic compounds. So let me first go to assessments, quizzes. I think these quizzes is the best practice there is for the test. Visible. Oh yeah, sizes. Sizes of ions. So we talked about visible to users. Let me get our periodic table up. In chapter 2, we were just talking about atoms and the periodic table. I said that as you go down row by row, you get bigger. So everything in this row is bigger than everything in this row. And everything in this row is bigger than everything in this row. You remember that? What's the trend when you go from left to right in one row?
Smaller?
Yeah, you get smaller. It's counterintuitive, but you've got potassium and the calcium is a little bit smaller, the scandium is a little smaller, and as you go across, same up here, as you go across, it gets smaller and smaller. The smallest thing in this row is argon. But it never gets to so small that it's smaller than anything up here. So everything in this row is bigger than everything in this row. But as you go across the row, they get a little smaller, a little smaller. When it comes to ions, we talk about gaining and losing electrons. So if you're looking at oxygen, it gains 2 electrons, become 2 negative, 1, 2. So the ion form of oxygen has a few more electrons, well, 2 in this case, than the atom itself, whereas metals lose electrons to become charged. So the thing about sizes in ions is actually very simple. Metals, they lose electrons, so they end up smaller than their neutral atoms. But non-metals gain electrons, so they end up a little bit bigger than their neutral atoms. Is that simple? Metal ions are smaller than their neutral form. Non-metal ions are slightly larger than their neutral form. Is that simple? I think the best thing to do is go to the end of this chapter and just go through some problems. I modified this a little bit. So I told you I'd give you these on the test. So use this as you go through the problems. Yeah, this is the other thing to mention. I'll give you this on the test too, but for instance, at the top there for the element chromium, if you have that's it, that's the formula. So what's the name of this? I've taught you already that, all right, so what's the charge on nitrogen? -3. Do this. So there's nitrogen. 1, 2, 3. It'll be -3. Did I not go down? Oh yeah, I didn't go to the problems yet. All right, so if this is -3 and there's only one of them, you've got a total 3 negative charge. That means you've got to have a total of 3 positive charges. There's only one chromium here, so instead of nitrate, you'll say nitride. So you can call that chromium-free nitride. There is this other naming system. I don't know why in science we have to have more than one. These are kind of antiquated. But if it's chromium-free, then you can call it chromic. So instead of chromium-3s, you could say that's what this chart is showing you. What's the formula for using this naming system? Chromium-2. What's the formula for that? Chromium-2 nitride. The other name here would be chromus. Spell that right. Oh, it is O-U-S. All right, fine, O-U-S. O-U-S, chromus nitride. So you're gonna have a chromium, you're gonna have a nitrogen. The question is, what are these subscript numbers? These happen to be 1 and 1. So if you've got a charge here of 3 negative and a charge here of 2 negative, or 2 plus, you're gonna need 3 of these and 2 of these to make it balanced. So the formulas look very different even though the names seem the same. Chromium-3 nitride versus chromium-2 nitride. There's chromium-3, there's chromium-2 nitride. And you can also call this chromic nitride, you can call this chromus nitride. So I'll give you that on the test too. I feel like this naming system is kind of antiquated, but you still see it sometimes, so it sounds very sciencey, chromic and chromus and cuprous. So just know that I'm giving you those, be able to work with them. I figure just those 2 pieces of information kind of rounds out this chapter. A bit about sizes of ions, a bit about properties of ionic compounds, and then that other weird naming system. Do you remember how to decide whether it's an ionic compound or a covalent compound?
Is ionic the metal and non-metal?
If it's got metals and nonmetals, it's ionic. If it's just nonmetals, it's covalent, as in molecules. What if it's just metals and metals? It's a metallic compound. Metals and metals is literally this stuff. Things you already knew of as metals before you took a chemistry class. So what should we do? Same kind of question. If you have potassium and oxygen, is that going to make a covalent compound or an ionic compound? Potassium is K. I have a few more of these. Anybody want one? I don't have a ton of them. This is the ones I printed before. Anybody else missed that?
Do we need another one, a blank one for the test?
Huh?
Do we need a blank one for the test, or are you gonna hand this
I'll give
out?
you a blank one. You can write notes on the one I'm giving you, but I'm gonna give you a blank one so you don't have your notes.
I'll take it back if you don't.
Anybody else
I'll
want
sit
one?
right here. Thank you.
Anybody else?
You can have this one.
Anybody else? Nobody else wants one? I'll keep, this is the same one that I keep bringing up. Just got it printed. Potassium. Here's potassium. What was it? Potassium and what? Potassium and oxygen. So here's potassium, here's oxygen. Is that going to make ionic or covalent? It'd be ionic because it's metal and a non-metal. 2 bromine atoms, what's that gonna make? No, bromine is over here, so covalent. Because bromine is a nonmetal and bromine is a nonmetal, so only nonmetals in that one. I think you can do those. What is the ion symbol for an atom with the given number of protons and electrons? 22 protons and 22 electrons. 22 and 20. So you look here, what's the first thing you're looking for? The atomic number 22. So titanium has 22 protons right here. 22 protons. 22 protons necessarily means titanium. If it's got 20 electrons, that means it's lost 2 electrons. So you look on the periodic table, you get Ti from there, and then you know it's 2 plus because it's lost 2 electrons. 22 protons, 20 electrons. You look on the periodic table, you find 22, you get the symbol, you also have the name there. And then if it's lost 2 electrons, that means it's going to be 2 plus. 17 protons, 18 electrons. Again, you look here, you look for 17. Chlorine has 17 protons. What does it say? 17 and 18 electrons. It's gained an extra electron. What did I say? Chlorine. If it's got 1 extra electron, then that's going to be the atomic symbol, or the symbol for the ion. The ion symbol. And you can do the same thing just backwards here. How many protons and electrons? So potassium has 19 protons, and you know that it loses 1 electron, become plus 1. So it's just going to be K1 plus. Oh, it gives you K1 plus. Doesn't it? Yeah, K plus. It gives you this. And you look at the periodic table to see how many protons it has. So protons is 19. Protons equals 19. It's lost 1. No, it's the number of electrons is 19 minus 1 because it's plus 1. So it'll have 18 electrons and 19 protons. Period 2 element that forms a plus 2 cation. Period 2, this is the first period, there's only 2 atoms in it. And the second period, that is the second row. The plus 2 ion that you'll get from this row is beryllium. So what is a period 2 element that forms a plus 2 cation? That one's going to be beryllium. Ion from group 2A with 36 electrons. This is 2A. Strontium has 38 protons and 38 electrons. It'll lose 2 of those electrons when it becomes charged. So it'll have 36 electrons. SR 36 electrons and 38 protons. You get the protons from the periodic table, but the 38 electrons in neutral strontium, you lose 2 of those to end up with 36 total electrons to get the 2 plus. The ion symbol for the barium ion, you just go to the periodic table, you find barium, which is here. Looking at the periodic table, you can tell it's going to be 2 plus. That's the ion symbol, which one was I looking at there? Barium ion. So these are good for practice too. I have questions like this in those quizzes, but thought I'd go here for extra stuff. All right, which noble gas? So the noble gases are on the far right of the periodic table. Trying to stick to the ones that you don't have answers to. It gives you the odd ones, right? It gives you those. Forgot what the question is. All right, let me just go back up here. I guess it's not giving you these answers, but oxygen, magnesium, aluminum. Sulfur. So oxygen's going to gain 2 electrons. So oxygen has, let's do protons. It has 8 protons. How many electrons does it have? Oxygen. How many electrons does oxygen have? Gains 2 electrons.
It's
10. Because it's 2 negative. It's gained 2 extra electrons. It gains those 2 electrons, and it now has the same electron configuration as neon. Electron configurations 1, 1, 3, 1, 3, 5. 8 protons, 1, 2, 3, 4, 5, 6, 7, 8. That's the electron configuration of neutral oxygen. When it gains 2 more electrons, it does that. It has 2 negative charge because it had 8 protons in it. Neon, 1, 1, 3, 5. Neon has 10 electrons. It starts out neutral with this electron configuration. You know, it doesn't gain or lose electrons to become an ion, so it doesn't tend to become an ion anyway. So this is the same as this for oxygen, but what I've given you here is oxygen 2 minus. It's got 2 extra electrons. That's why it's charged. Oxygen has 8 electrons and 8 protons. 8 protons, and neon has 10 protons. So it's neutral when it's like this. When oxygen is like this, it's -2 because that's 2 extra electrons. So it ends up with the electron configuration of neon, but it's still charged 2+ because the number of protons is different. Magnesium is over here. When it loses 2 electrons, become +2, it also ends up with the same electron configuration as neon. gets there by losing electrons from up here. It's got those two electrons. Magnesium does. But it loses those two electrons and ends up with that same configuration as neon. Aluminum is here. It loses 3 electrons and it becomes just like neon. So all 3 of those have the same answer. Oxygen gains 2 electrons and becomes neon. But it doesn't become neon, it has the same electron configuration. Magnesium loses 2 electrons and ends up with the same electron configuration as neon. Aluminum loses 3 electrons and ends up with the same electron configuration. Here's sulfur. If it gains 2 electrons, what does it become like? This one will be like argon. There's sulfur. It gains 2 electrons, it becomes electron configuration of argon. It doesn't have the same number of protons as argon, and that's how it ends up being charged. Two negative. That's those types of questions. I want to get to. I'm not sure if I gave you questions like this. I don't think I did, so let's go. This one, 3.43, I guess it gives you the answers. But 3.43 is asking you, identify the polyatomic ion and give its charge. All right, this one, that question purposely gave you some that aren't in that chart. There are other polyatomic ions besides the ones that we're working with. And I won't make you know the names or charges of those, but here you can infer it. So if you look at this first one, A, the positive ion is always on the front of the formula, and then the negative ion is the next. But if you pulled apart what you're looking at there, you see Na, and the name of that one is chlorite. ClO2. Yeah, it's not asking you for the name of this, but it's telling you to identify it. So you can immediately go, there's the positive ion, right? So you know the rest of that. You know that you know that's the polyatomic ion. The question is, what's the charge? Well, if I pull these apart, I put NaOA over here separate. What's the charge on Na? Periodic table over there. What is it?
+1.
So it's +1. I could put a 1 here, but we always omit the 1. That means this has to be negative because there's not a parentheses around here with some number here. So you know there's only 1. So that's the polyatomic ion, and its charge is -1. So where's the metal? What's the metal here? And what's its charge? It's +3. Okay, so there's 3 OCNs. Those are the polyatomic ions. If there's 3 of these, what's the charge on each one?
On the -1.
They together add up to -3 because there's 3 of them. So here, the polyatomic ion is OCN. I guess that's cyanate. And then the charge is -1. Those two aren't on your chart. I won't expect you to know those names. They kind of do it again down here. For 3.44a, K is the positive ion. And that's going to be +1. That means BrO3 is -1. That's a polyatomic ion, BrO3. Bromate. HPO3 is on your chart, but you can figure it out from here. What's the charge on calcium? +2, so HPO3 must be -2. It is on here. I'm sure. Is that HPO3? Yeah, so I guess it's not on there. But HPO3 must necessarily be a -2 charge because calcium was +2. HPO3. So you can infer charges from the charges you know. If I split those out. So this has to be a 2 negative polyatomic ion. All right, write the formula for the ionic compound from each pair of elements. So calcium and sulfur. Do this. Calcium and sulfur. No, let's do the even ones, just so you have 3.45 to practice. Barium and bromine. Aluminum and sulfur. Read those other ones to me after aluminum and sulfur.
Lithium and iodine, nickel and chlorine, sodium and selenium.
Sodium and what?
Selenium.
I'll do calcium and sulfur too. I wanted to do that so I could have the periodic table here. Write the formula. We'll do the formula and the name. What's the charge on calcium? 2 plus. Barium? Aluminum?
3 plus.
Y'all can just look here and see that, right? That's a big cheat sheet, and you get one on every chemistry test, so don't miss how to do this. Lithium? Okay, +1. Nickel is down in the transition metals. Or it might even be down here. There's nickel. So we won't try to put a charge on that one. Sodium? Sulfur? What is it? 2 minus bromine? Not 2.
3.
No.
2 plus.
No,
-1.
it's 1. When you're on this side, this is a little tricky. When you're on this side, let me start on this side. What's the charge on magnesium? You look at magnesium and you touch it and you go 1, 2. Charge +2. When you're on this side, oxygen, what's the charge on oxygen? I'm not going to touch oxygen. I'm going to skip oxygen. I'm going to go to the right and go 1, 2. You see the difference? So these are all -3. These are all -2. These are all -1. So where were we? Bromine is here, so what's its charge? -1. Sulfur is here. You don't count sulfur. You go 1, 2. So sulfur is 2 negative. Iodine is here. -1. Chlorine is here. Selenium is here. So minus selenium is 2 minus. So now we have all the charges. These aren't the formulas. I just have them listed here. Calcium and sulfur can go together like this because their charges match. barium and bromine, you're gonna need 2 bromines to match the charge of barium. This is the one that I said is a little tricky. You're adding up to 6 here, so you need 3 of these to add up to 6, or 2 of these to add up to 6. It's kind of like least common multiples. These are 1-to-1, so it's just LiI. There's only 1 nickel here. Oh, wait a minute. Yeah, let me skip that one. We're going to need 2 sodiums to add up to selenium. So this one is Na2 Se. Question. Nickel and chlorine. Write the formula for the compound. All right, let me look. Get another iteration of our test book going. Nickel might be one of those that they act like only makes 1 charge. So I won't include it. I wouldn't include nickel here because you can't really know the charge on. If it's a transition metal, you have to be told the charge. So, and they're not telling you the charge here. They're assuming it has a constant charge, but I won't ask you what that on the test. So they're saying nickel 2+. So this one would have to be nickel 2 chloride. But you would have to be told the charge on nickel somehow. So those would be the formulas. What about the names? What would be the name of this? It's got calcium and sulfur. But you leave that name the same and you go sulfide. This is barium bromide, aluminum sulfide, lithium iodide, and sodium selenide. So those are the names. Oh, you read me these. You read me. Oh, no, that's the even one. Let's do zinc and sulfur. And magnesium and fluorine. Zinc. You'd have to be told the charge on zinc. So magnesium and fluorine. For one thing, we can just go ahead and say magnesium fluoride. But what would be the formula? What's the charge on magnesium and fluorine? So we're going to need 2 of these, so it'll be Mg. So MgF2 is the formula. The name is magnesium fluoride. Except for the math part of the test, I think everything will be multiple choice. It's hard to do the math part multiple choice. So in 3.51, they're just using M in general as naming the metal. It's asking for the charge on whatever random metal that might be. No, that's the odd one. I want to do the even one. Right? You get the answers to the odd ones, right? MCl2. What's below MCl2? Just read them to me. MO. What else? All right, so what's the charge on the metal? Here you infer the charge on the metal from the charge on the non-metal. What's the charge on chlorine? You might have said it, I just didn't hear you. What's the charge on chlorine? I should say chloride, charge on chloride. What's the charge on oxygen or oxide? O2, nitrogen or nitride. All right, so if there are two of these, the charge on the metal is what? Because there's two of them. Metal has to be 2+ in this case. This metal, what's the charge on this metal? There's only one of these. If I only have one -2 charge, then this one metal has to be a +2 charge to make this neutral. I have 3 of these. I have a total of, I'll say 6 negative. I have a total of 6 negative because I have 3 of these. 2 times 3 is 6. I have a total of 6 negative. I have to split that 6 negative among 2 different metals, or they're the same metal. But for those 2 charges, that charge and that charge, to add up to +6, what's the charge on the metal? Y'all see that? The answer here is 2, well, I guess 2+. The answer here is 2+. The answer here is 3+. What is the charge on the metal? Not what is the total charge on the metals here, what is the charge on any individual metal there. So we split the +6 into 2 +3. Charge on nitrogen is 3. There's only one of them, so we have a total of 3 negative for our charge. We have 3 metals, and they're going to be charged positive. So what's the charge on the metal? +1. So the answer here is +1. You see that? Inferring the charge on the metal, and then if there's more than one metal, you've got to split the charge among them. You can come up with a formula and the name for these. But let's go to 3.54. It's K and G. And what's the last one? Cl. Cr, chromium, Cr. So what's across the top? ICN. What else? HPO4, SO4. I think the charges, which chromium, 3. I is negative, Cn is negative, you can look that up on that chart. NO3 is negative, and then SO4 is 2 minus, and HPO4 is 2 minus. So what's the formula for Ki? I just gave it to you. 1 plus charge, 1 minus charge, we can put them together like that. Magnesium and iodine, there's 2 plus charges here, plus 2. So we need 2 of these to balance it. And for Cr, we'll need 3 negative charges to balance that. 1 plus and 1 minus, so these kind of come out the same. That'll just be KCN. This one will be Mg. We're gonna need 2 CNs, so I'll put it in parentheses like that. You guys with me? So 2 and 2, this one's gonna be, make it balance. You following? -1, +1, so this is just KNO3. You're gonna need 2 NO3s here, so two NO3s to balance the +2. And here we're gonna need 3 to balance. You with me? So those are the formulas. So now we have SO4 that's 2 negative, and we only have +1 here, so this is actually K2 SO4. This one is just MgSO4. Because 2 plus and 2 minus, those already balance. This is where we have to think in terms of 6. So Cr2 2 of these and 3 of those, that'll make it balance. Cr2, SO4, 3. This one has to be K2 and HPO4. This one is just Mg, HPO4, and then Cr. That's how all those would be. All right. Naming these. So the positive ions, it's always the metal. Let me go here. It's always the metal that you have to decide whether you have to do a parentheses. If it's in this column, far left column, or this column, column 2, or aluminum, you don't need the parentheses. Any other metal, you're going to need the parentheses. But potassium's in that first row, magnesium's in the second row, chromium is one that's down in here. So we need a parentheses to name these. But let's name these other ones first. What's the name of this one? K is potassium. Potassium what? Iodine. Rather than iodine. What's the name of this one? It's magnesium what? You're saying iodide? You're not saying diiodide, correct? It's just iodide. You might wonder why I say that, but it's when we name the covalent compounds that you use those di, tri, like, let's say, I can't even think of something off the top of my head. You'll see what I mean. But here we're gonna go Now we need a parentheses, iodine. What goes in the parentheses?
Mercury.
A 3. Chromium 3 iodide. Um, There's also this other naming, you can call that chromic iodide. If you look up CN, that's called cyanide. If you look this up, it's nitrate. This up, it's sulfate. And this is hydrogen phosphate. I said I'd give you this on the test. I'm just getting those straight off of here. CN negative is cyanide. What else is there? Nitrate and sulfate. There's nitrate in O3, and there's sulfate, SO4, and HPO4 is hydrogen phosphate. So I just got those straight off of there. So this one is chromium 3 cyanide, chromium 3 nitrate, chromium 3 sulfate, this one was once you specify that 3, that's why you don't need tetra here for the 3. Do that right? Yeah. 3 of those for 3, 3 of those and 2 of those. 2 times 3 is 2, 3 times 2. Yeah, that's right. Chromium 3 hydrogen phosphate. Potassium cyanide, potassium nitrate, potassium sulfate, potassium hydrogen phosphate, magnesium cyanide, magnesium nitrate, magnesium sulfate, magnesium hydrogen phosphate. But chromium's the one that needs the parentheses. You with me? What's the name of this one? K is potassium. Potassium what? Potassium fluoride. How about this one? AU is gold. And I told you that you have to be told on the transition metals. Transition metals and the ones in the bottom right. What did that say? AuPr3. AU is gold. So if you look on your periodic table and you find AU, you'll find gold. I need a parentheses for it. I'm going to say bromide. But what's the charge? So you're not explicitly told the charge here, but you have to infer it. Yep, so Br is charged -1, and if there's 3 of them, that means we have a total of 3 negative here. So we need a 3 positive to balance it. There's only 1 gold here, so all 3 of that charge comes from that 1 gold, so that's gold 3 bromide. Can you name this one? SN is 10. So that's 10 parentheses bromide. What's in the parentheses? It's a 4. Charge on bromine is -1. There's 4 of them, so there's a total of -4 charge there. Oh, and you would write that Roman numeral 4. The other naming system is Stannis and Stanic. There are more than these. Like for gold, there's Auric and Auris. But like I said, these are kind of antiquated. Books still include these because this shows up a lot on chemicals in a stockroom. What else can we do? Let me remind you of this. All of these polyatomic ions, notice they're all negative. Every one of them are negative. They're going to be on the right side when you write it in the formula. When you write the name, it's going to be that last name that you write. There is a small handful of positive ones. That's positive in H3O. This is I think the only one to worry about for the test, just memorize that one because it's not in that chart. But that one will go on the front because it's positive. Hydronium, that just doesn't come up. I swear there's one I'm forgetting. It'll pop up next semester. But there's a very small number of positive polyatomic ions. The vast majority of them are negative. So just something to know. So when we get here and you see NH4, you've got that on the front because it's charged positive. SO4, if you look on here, SO4 is here. Sulfate, it's 2 negative. So if that's 2 negative and there's only one of them because there's not a parentheses with a number on it, and there's 2 of these NH4s, that's because NH4 is 1 plus. So that's why the formula looks like this. The name of this would just be ammonium sulfate. You don't need a parentheses because ammonium is a polyatomic ion with a known charge. It's not a variable charge. I think you could name these. HPO4 is hydrogen phosphate. Let's look here. Hydrogen phosphate is 2 negative, HPO4. HPO4. So if that's 2 negative, and there's 2 of them, and SN is 10, is that the one I just did? I must have just done that. No, that was bromide. Well, I'll just say it. This one will be 10,4 hydrogen phosphate. Because you've got 2 of these, and each one of them is charged -2. So you gotta have a +4 over here. So that would be 10,4 hydrogen phosphate. 3.68D would be 10,4 hydrogen phosphate. 10 with Roman numeral 4 in the parentheses. I think you could do those. So how about these? Is this true or false? Ionic compounds have high melting points. It is true. They have extremely high melting points. In fact, they pretty much only exist as solids in the pure form. Ionic compounds can be solid, liquid, or gas at room temperature. False. They can be solid liquids or gases. You just have to have extreme temperatures to get them liquid, and even more extreme temperatures to make them gases. But at room temperature, no way. Most ionic compounds are insoluble in water. Most. I don't even think you can say most are soluble. I won't ask you that on the test. Just know that some are soluble, some are not. That's kind of like non-information, right? But not all of them are soluble in water, and none of them are soluble in water. I don't think most ionic are insoluble. I think that's probably true. Let's not trust that one. An ionic solid like sodium chloride consists of discrete pairs of sodium cations and sodium anions. Yeah, that's true because it's a 1-to-1. Sodium chloride would just be NaCl. So yeah, you have Na plus, Cl minus, and then in the crystal you have Na plus, Cl minus. And you could say that it's made up of a bunch of pairs. That's an odd way to put it. There really isn't much to these. Let's look at this before time runs out. I did put in here. I just opened them. Test 1, test 2. I opened a few more of these, so I think we're complete for chapter 3. And it's the vocabulary and conceptual that I've added a little bit of that type of information. Preview. Let's just see what kind of questions are here. I don't think any of them are tricky like that. Do you remember what the electrons in the outermost occupied shell are called?
Valence.
Valence. The blank rule states that a main group element is especially stable when it possesses 8 electrons in its outermost shell. It's called the octet rule. Bonding for main group elements, that's the first 2 columns and then all the nonmetals. Main group elements gain, lose, or share electrons to attain the blank of the nearest noble gas neighbor. You know what word you would put here? Yeah, electron configuration. We've talked this chapter about gaining and losing electrons, thereby making ions, thereby drawing the atoms together, really the ions together. The sharing of electrons is the next chapter, that's covalent. But when sharing electrons, they do the same thing. They end up having enough electrons in their valence shell to be like a noble gas. Blank or negatively charged ions and blank or positive. Blank or negatively charged ions and have blank electrons than protons. If it's negatively charged, it's got more electrons than protons because the electrons are charged. So it's going to be more. And negative anion or cation? Anion. Cations are positive. The cat has pause. Which statement concerning lithium ion is correct? Lithium has 2 total electrons. This one might be a little tricky. Lithium has an octet of 8 electrons in its valence shell. Let me do this real quick. Here's lithium. 3 electrons for neutral lithium. And if I did the electron configuration, 1, 3, 1, 5, really there's one more 1 right here. The 4s shows up right here. Lithium has 3 though. 1, 2, 3. And it's talking about lithium plus. So it has lost this electron. That's the electron configuration of lithium. It does obtain the electron configuration of a noble gas, but it's helium, and it gets a number. That's the electron configuration of helium as well, 2 electrons. All right, so now look